Now the topic we are going to learn is about matrices. This is a chapter of determinants, but we are going to learn about matrices now. So what is the adjoint of matrix here is, that is all about the definition. So we'll see what is going to be the definition. So if you consider maybe a particular matrix, so I'll consider a 3 by 3 matrix only for a better understanding. So it is going to be A11, A12, A13, A21, A22, A23 and A31, A32 and A33. Okay, this is all about the particular matrix B. So if you are going to find the adjoint, we represent the adjoint of matrix as ADJ of the matrix B. So adjoint of a matrix is also a matrix. That's the first thing we need to know. Adjoint of a matrix is also a matrix, not a determinant or something like that. So it is going to be according to the definition of the adjoint of matrix, it is going to be like this. This is the cofactor. So this is A21, A31, A12, A22, A32, A13, A23, A33 whole transpose. This is the transpose, or it could be T also. T represents the transpose over here. So what is the definition of this particular, that is the adjoint of a matrix is a matrix of the, it is a transpose of the matrix. Okay, first of all we consider transpose now. Transpose of the matrix that is containing the particular cofactors of that element. Here 1 1, here 1 1. So the transpose of this transpose is very important when it comes to the solving of the question. Many of us just miss this transpose and land up in very wrong answers. So it is going to be transpose. Transpose is very important, very important. Okay. So if I consider the transpose, I need to take the middle line and just interchange these things. So or it is, I can write it to be A11, A12, A13, A21, A22, A23 and A31, A32, A33. Okay. So whenever we found out any definition, we always did the finding the properties of these things. So that is a theorem which says about the property of this. So if I multiply these two things, what I am going to get? So if I multiply this matrix with this, so we are going to get it in such a form that all the diagonal elements are going to be equal to the determinant, value of the determinant. So if I write B into adjoint of B, it is going to be the determinant value of B. That is all about the property of this, or its commutative is also equal. That's all about the property. Okay, we'll just take a general form of 2 by 2 matrix here. So we are going to find the adjoint of that. There is a very shortcut method for finding the adjoint of this A. So what is going to be the adjoint of this particular A here is, first of all we need to interchange these two things. Okay. So the diagonal elements, we are going to consider the diagonal elements. Step 1, interchange the diagonal elements. Okay, we are going to interchange the diagonal elements. So what are going to be is, okay, we'll just write adjoint of A here. Okay, if I interchange, this becomes A22 and this becomes A11. Okay, then what is the step 2? Step 2 here is change sign of the other two elements. So since it is a 2 by 2 matrix, there are only 4 elements. Other than the diagonal element, there is only 2. Therefore, the change the sign of the other 2 elements. Therefore, it is going to be minus A12 minus A21. This is all about finding the adjoint of that A. So this is very simple, right? Instead of finding the other one. Now we are going to learn about the classification of square matrices based on something. Okay, so based on the determinant, because it's about determinant chapter, so we are going to do something with the determinants now. So A, so maybe a matrix, square matrix only we are considering. So if it is a square matrix can be either singular or non-singular. Okay, singular and non-singular. What is the meaning of the here? If it is a singular matrix, that is a square matrix, it is told to be singular if the determinant value of that is equal to 0. Okay, so this is going to be the opposite. Determinant value is not equal to 0. If determinant value of A is not equal to 0, then A is said to be a non-singular matrix. That's all about what is singular and what is non-singular. Okay, so if you consider the product, okay, so we are considering only the square matrices here. If you consider the product of these, maybe two square matrices, A into B and B into A. Okay, maybe it is not commutative. I am not going to equate it here. So if A and B are non-singular matrices, then this product, that is AB and BA, are also non-singular. Okay, that is one theorem, that is one point here we are going to learn based on this. Okay, that is, if A and B are the square non-singular matrices of the same order, then AB and BA, that is the product of these two matrices, is going to be non-singular only. It cannot be singular over there. Okay, next you have the second point. In the second point, it states that the determinant value of AB is equal to the determinant value of A into the determinant value of B. If A and B are square matrices of the same order, okay, if they are going to be the square matrices of the same order, only then the product of these two, the determinant of the product of these two, is going to be the determinant like this. Okay, so better we need not to consider the singular. Even if you consider the singular, we are going to get the determinant value of this is 0. So both the sides are going to be 0 there in such a case. If it is non-singular, that is not going to be the case. Okay, that's all about this. So now we are going to do something else now. So instead of finding something, okay, we'll find like this. So maybe det of adjoint A. Okay, we are going to use this property and find out this. And this property also we need to use in that case. So first of all, we find adjoint A into A. Okay, from this one we found out that the product is going to be the I into this. Okay, if I consider the determinant of I, it is going to be 1, therefore I can just exclude that, and it is going to be the determinant of A. Okay, that's all we got here. So if I consider this thing and I remove this B outside, but still we are asked to find not like this. Since we have found out the determinant of the whole thing, so I need to consider this matrix not simply like this. So it is like this: 0, 0, then 0, det A, 0, and 0, 0, det A. Okay, like this we are going to get. So by using the properties, we know that we can remove any common factor from a particular row or a particular column. Okay, right? That's what we learned in properties. Therefore, these three, from these three rows I am going to take, it becomes modulus of A whole cube, then 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, that is going to be 1, however, this is going to be 1. So this is, if I consider A and B, where A is a non-singular matrix, we are considering non-singular only. So if A is a non-singular matrix, A into B, B is something else here. So this product becomes det of adjoint A into det A. Okay, since this is 1, I can just remove that. Then you have cube, this becomes square. Therefore, det of adjoint A is equal to det A square. Why has that square come over there? So if we consider, maybe this I have taken the order to be 3. Yeah, I have taken the order to be 3. If it was order 2, then I would have got det A only, right? I would have got det A only in such a case. So therefore, I can just conclude for a general, that is det of adjoint A is equal to det A raised to n minus 1, where n is the order of A, order of the matrix A. So if n is the order of the matrix A, det A whole raised to n minus 1 is equal to the det of adjoint of A. That's all about the properties. Okay. So in the heading we also have one inverse written over there. So we have already learned what an inverse is in the previous chapter by finding that long method that was the elementary transformation and big things over there. So how that adjoint of a matrix is connected with the inverse, we are going to use this same property over here. Okay, we are going to use the same property over here also. So what we are going to do, so maybe we will take a matrix A into adjoint of A is equal to A into I. Okay. So what is the definition of a particular inverse? Is A into A inverse is equal to I, or vice versa I can write A inverse into A. This was the properties we learnt in relations and functions, first chapter. So this was the identity element. So this is called to be the inverse of this element. Okay. So here it is a matrix, not just element. So what we are going to find out is here inverse of this. So we have one I here, we have one A here. So somehow we need to get this A inverse. So that means A inverse is somewhere hidden over here. So for that, since I know that this det A is just a value, so while defining a determinant, we told that the number or the value that is corresponding to a particular matrix. So this is just a value or just a number. So I can write A into, because I can just transpose this here, it comes to be adjoint of A divided by det A is equal to I. Okay, this much we got. So this comes to be same as this, right? This comes to be same as this. So I can write this to be A inverse. Therefore A inverse is 1 by det A into adjoint of A. This arises the use of adjoint of A. Okay, that's why we find out and so many things. So for finding adjoint of A, we need the cofactors over there. So that's why we learned about cofactors. For learning cofactors, we needed minus. So minus we learned before that. That was the meaning of minus. We find out the inverse of a particular matrix. So for an inverse to exist, this det of A should be a positive or negative or any value. It cannot be 0, where det A is not equal to 0. So if you consider det A is equal to 0, there are some other cases. We are not going to learn about that. We are going to consider only when det A is not equal to 0. Okay, when det A is not equal to 0, we are going to get a number or any real number we are going to get, and we are going to get a particular matrix. This adjoint A is a matrix and this is also a matrix. So this is going to be, however, the thing what we are going to get. So we can just tell that every singular matrix cannot have an inverse. Yeah, every singular matrix cannot have an inverse. So in the previous chapter we also found out one example, one of the exercise questions where all the elements of a particular row or a column become 0 while doing elementary transformations. In such a case we concluded that the inverse did not exist for that particular thing. So this was the reason. This was the reason, that is the determinant of that became 0. That's why we understood that it was not going to have an inverse. That's all about the inverse of the matrix. So next we'll learn how to find out the inverse of the matrix, adjoint of the matrix, in the coming chapter, coming exercise. Okay, now we are going to start with exercise 4.5 here. So this first question is very simple, because I had already told the two steps, that was interchanging diagonal element, changing the sign of the other two. That was all about finding the adjoint of a 2 by 2 matrix. So we are going to now see how we are going to find adjoint of the 3 by 3 matrix. So if I name this to be A here, what is going to be the adjoint of A? Okay, the first thing we are going to mark here is the transpose. Otherwise we forget that transpose is very important. Okay, this is going to be the transpose here. So finding the cofactors of this. So 3 into 1, that is 3. Then you have 2 into 1 is 2. Minus of minus 10. 2 minus of minus 10 is 2 plus 10 or 12. So since it is this position, you are going to give a negative sign over there. Then now you have 2. 2 into 0 is 0. Minus of minus 6 is 2 into 3, going to get 6 over there. Okay, similarly we are going to get 1 into minus 1 is minus 1. So again a negative sign we need to give, because it is 2 plus 1 here, right? Second row, first column. Then you have here 1 into 1 minus of minus 4. 1 into 1 is 1 plus 4. 1 plus 4 is 5. We need not change the sign here. Next you have minus 2 into minus 1, that is 2. Give a negative sign for that, because it is minus here. So it is minus 2 over there. Since it is this position, again a negative sign need to give. So it comes to be 2 only. Okay. Next you have minus 5 minus 6, that is minus 11. Directly you can write. Then you have 1 into 5. 5 minus 4 is 1. Since it is this position, I need to give a negative sign here. Then you have in this position 3 minus of minus 2. Yeah, that is 3 plus 2, that is going to be 5. So we need to find the transpose of this. It is going to be 3 minus 12, 6, 1, 5, 2, minus 11, minus 1, 5. Okay, that is the value of the adjoint. So similarly you can do the third and the fourth question. There the extra thing is just you need to multiply this adjoint with the given matrix and show that it is equal to the determinant of A into I. That property we are just asked to prove. So next we are moving on to the questions from 5th to 11th. So simple ones I am going to skip. I am going to start with the 6th question now. Okay, now we have our 6th question here. 6th question is about A, that is a 2 by 2 matrix. So I am going to do it fast. So it is adjoint of A. Adjoint of A, we need to just interchange this. This is going to be 2, here minus 1, here minus 5, and here 3. That's all about the adjoint of this. So what was the determinant of this is minus 1 into 2, that is minus 2, minus of minus 3 into minus 3 into 5 is minus 15. Therefore it is equal to 15 minus 2, that is 3. Therefore A inverse is equal to 1 by 13 into 2, 3 minus 5 minus 1. This is all about the 6th question. Moving on to the 7th question now. Okay, now we have a 7th question. Here first of all we need to find the adjoint, however. So I put the transpose symbol first itself so that I can't forget that. So it is 10 here. Then we have 0 into 0 again 0 here. Then you have 0, 0, 0, everything 0 here. Okay. Then you have here 10 again, but it is negative sign here. Then you have 5, then 0, okay, 3 zeros over, I think, no more zeros mostly. And then we go to this element, that is 8 minus 6, that is going to be 2 here. Then we have 4, since it is coming here, one negative sign should be there. Then we have 2 here. Okay, this is all about this. So this adjoint becomes 10 minus 10, 2, 0, 0, 0, 5, minus 4 and 2. This becomes the adjoint of A. So what is going to be A inverse is, first of all we need to find the determinant of this A. So easiest method is, I can start with this first column. If I start with the first column, these two goes to be 0. So it is going to be 1 into the cofactor of that is 10. Okay, it is 10 only. So it is 1 by 10 into this determinant. That is 10, 0, 0, minus 10, 5, 0, 2, minus 4, 2. This much is okay. This is all about A inverse 7th question. Next we'll move on to the 9th one. Okay, let me take the 10th question. Okay, now we have a 10th question here. 10th question is like this. So we are asked to find the inverse here also, if it exists. So we'll go to the 10, how it looks. Okay, we need to find the determinant value first of all. So it is given if it exists, so maybe determinant value, we'll just check it out first. So let me expand using this because one of them is 3. So it is 1 into 8 minus 6, that is 2. Okay, then we have 3 here, that is plus 3 into 3 minus 4, that is minus 1. Okay, so minus 1 is going to be the value of the determinant. So need not worry, there is no 0 over there. So 2 here, since it was like this. So the value of cofactor for that was minus 1. So I can just enter that itself. Then we consider the 0. It is going to be minus 4. Minus of minus 4. Again 0 only here also. Okay. Next we have this particular term. For that we have 0 into 4. Minus of minus 9. There it is going to be 9. Since it is this position, I can write to be minus 9 over there. Okay. Then we have this point. If I consider that point, it is 1 into minus 2, that is minus 2, minus 2 plus 3. Minus 2 plus 3 is 1. So 1 you need to enter here. Okay, similarly we are going to do 4 minus 6, that is minus 2 here. Then we have minus 2, minus 3, that is minus 5. Since it is in this position, minus 1 more sign here, right? Then here we have minus 3. So since it is that position, I need to change the sign. Then we have 2 here. Okay, this is all about this. So what it is going to be is 2, 0, minus 1, minus 9, minus 2, 3, 1, 5, 2 is going to be the adjoint. Okay, therefore the inverse is going to be minus 2, 9, 1, 0, 1, 2, minus 3, minus 5, minus 2. Okay, wherever positive sign was there, I just put the negative sign. Wherever negative sign was there, I changed it positive because it is 1 by minus 1 over there. Okay, that's all about finding the inverse here. Next we'll move on to the 11th question now. Okay, now we have our 11th question. 11th question is a little bit different when compared to the other ones. So here you have like this. So first of all we need to find the determinant value. I have just written it directly here instead of making one more step over there. So I just will find out the adjoint here itself. So what is the determinant value of this? Minus cos square alpha, because it is like this, minus sin square alpha. That is going to be minus 1. If you take minus sign outside, you get cos square alpha plus sin square alpha. That is going to be 1. Therefore it is minus 1. Okay. So it is going to be minus 1. I need to enter here. That means every element that is present here, I need to change the sign over there at last. Okay, we just think about that later. So this is going to be minus 1 here also, because this was directly the cofactor of this particular element, because it was simply 1. So there was no problem. So directly I carried it to be minus 1 itself. So we consider this element now. It is going to be 0 into 0, 0, everything 0. Similarly, this also becomes 0, I think. Right? Yeah, 0, 0. There are two zeros here. That's it. So we consider this position. If I consider this position, there are two zeros here. Therefore, this also becomes 0. If I consider this position, there are two zeros here. Considering this determinant, again 1 0 comes here. Okay, those things are gone. Next, only these four elements are present over here. We need to take what we need to do. Okay, we'll consider this point here. This is going to be minus cos alpha plus 0. So it is minus cos alpha itself. Okay, since it is this position, we need not change the sign. Okay, we'll think about this now. So what it is going to be here is, we'll see what it is going to be. Sine alpha will change this, which is going to be 1 into sine alpha minus 0. That is sine alpha only. Since it is this position, I need to write minus sine alpha. Okay, then we have here, if you consider this position, we need to change the sign later. So this becomes 1 into sine alpha only. That is sine alpha, one negative sign over there. Okay, then we have this position. If you consider this position, you are going to get cos alpha there. Okay, we need to take the negative sign inside and find the transpose of that. Since the transpose is equal, I need not bother because the diagonal elements do not change. These elements are equal, right? Therefore, this transpose is not at all required over there. Then I'm going to consider the minus sign. So 1 0 0 0 0 cos alpha sine alpha minus cos alpha. Okay, this much is all about finding the inverse of the 11th question. Next, we'll move on to the 12th question. See, the 12th question is you have an example question very similar to that. There is example 25. So we need to just take the same method on doing that. Since it is 2 by 2 matrix, finding the adjoint is very easy. So I'm going to skip that question also. Next, we have the 13th question. 13th question is also present as a question 8 in the miscellaneous exercise of chapter 3, that is in matrices. We had already done that question, so we need not do that question again. Moving on to the 14th question now. Okay, now we have a 14th question. So from seeing the question, I can infer that this does not involve anything about adjoint, neither of inverse. This is a question simply based on matrices. Okay, maybe I can just do it faster. What is a square is 3 1 2 1 into 3 1 2 1. Okay, we'll just multiply and see. It is going to be 9 plus 2, that is 11. Okay, then we have 6 plus 2. Okay, 6 plus 2, 6 plus 2 is 8 here, so 8 comes here. Then we have 3 plus 1, that is 4. Then again we have 3 here. This is a square. So then to just somehow get that. Okay. So if I add all of these things, what I am going to get? So we'll just do what is this equation. So this equation says 11, 8, 4, 3. This is the matrix plus A times. So I'll take A everywhere inside. This is 3A, this is A, this is A, this is 2A. Okay. Then you have the identity matrix. Identity matrix has 2 zeros here, and this becomes the B, equating it to 0. That means that if I add everything here, if I add everything over there, it is going to be equal to 0. So maybe we're going to take these terms. Okay, that is 4 plus A plus 0. That is 4 plus A is equal to 0. Okay, or 8 plus 2A is equal to 0. Both give the same. Therefore, A is equal to minus 4 is the answer for this. Okay, similarly we have 11 plus 3A plus B. That is the first. Okay, if I equate all of them, it should be equal to 0. Then minus 4 into 3 is minus 12, therefore it is minus 12 here, plus b is equal to 0, so b is equal to 1. That is the answer. So b is equal to 1, a is equal to minus 4 is equal to the answers. So corresponding to the questions 15 and 16, such type of questions cannot occur in the board exams since it is very long to do that. So better just skip that question. Moving on to the 17th question. If we see the 17th question now, it says let A be the non-singular matrix of order 3 by 3, then adjoint of A is going to be how much? So that was one of the properties we found out, that is adjoint of A. Det of adjoint of A is going to be det A whole raised to n minus 1 when n is the order, where n is the order of that particular matrix. So here it is considered order is 3, this is equal to 3, therefore it is going to be det A square. This corresponds with option B. Okay. Next we'll move on to the 18th question. 18th question is a little bit twisty here. So if A is an invertible matrix refers to that it is non-singular. Okay, then it is given order is equal to 2. N is equal to 2, that much is given. And then you are asked to find the det of A inverse. Okay, so if we find the det of A inverse, it has to be det of adjoint of A divided by det A. Okay, first of all we'll find out what is there inside. So we'll take an example, that is A, B, C, D. Okay, and then what is going to be its adjoint is D, A here. Then here minus B, here minus C. This much we got. Okay, that's all about this. So what is going to be the determinant? We'll just leave it as it is, that is 1 by determinant, like that only. So what should be inside this determinant is a matrix. Okay, so adjoint of A divided by det A is going to be B by det A minus B by det A minus C by det A and A by det A. Okay, this much we got. So this was det of A inverse. Det of A inverse. Okay, so from this we can find out that 1 by det A is common in both these. Okay, 1 by det A is common in both these. So I can remove 1 by det A 2 times, 1 by det A 2 times, because it corresponds to one row and the second row also. Then what you remain here is D A minus B minus C. Okay, here order is given to be 2, and when we compare this and this, they are equal, right? They are the same, therefore it is corresponding to det of adjoint of A. Okay, we knew that det of adjoint of A is det A into n minus 1, A raised to n minus 1. N is 2 here, therefore it is going to be det A only. Therefore it is 1 by det A whole square into det A. Here we are going to get cancelled. So 1 by det A is the answer. And 1 by det A answer is given in option B. That's all about adjoint of a matrix and inverse of a matrix. That's all for today. In the next class, we are going to learn the application of using this inverse in some statement problems and solving a system of linear equations in x, y, z if you have 3 variables and such things. That is the last topic of the exercise, and then we move on to the miscellaneous exercise with special type of questions, different type. So